In this video, I will introduce some compartment models of how a drug interacts within your body. So suppose that a drug is being introduced into your body at a rate we'll call d of t. So this could be a continuous rate, such as an IV or something like that, or it could be a discrete rate if you're taking individual doses. So this is the drug introduced into your body, and immediately it will go into the bloodstream. So the first compartment in this model is going to be the bloodstream. And then we're going to transfer that drug from the bloodstream to another compartment, let's say your brain. So our assumption is that the rate at which the drug flows from the blood to the brain is proportional to how much drug there is in your bloodstream. That constant of proportionality will be K12. Now, the drug that's in your brain will also be absorbed back into your bloodstream at a rate proportional to how much of the drug is in your brain, and that will be at a rate we'll call K21. And so this is a simple two-compartment model of a drug interacting in your body. Once the drug is back into your bloodstream, it could be eliminated from your body, probably through some other system of your body, and we'll say that that's at some rate. We'll call it K. So using those assumptions, we will say the amount of drug that's in the bloodstream will be given by the X1 equation. So here, let's go ahead and call this compartment X1 and this compartment X2. And so the rate of change of the amount of the drug in compartment X1 is dx1 dt. It leaves the bloodstream at a rate proportional to the amount in the bloodstream. So this is the amount of drug that's kind of being absorbed into your body and then leaving your body. So that's minus K times X1, referring to the arrow that's just above this equation. And then some of the drug is moving from compartment 1, the blood compartment, to compartment 2, the brain compartment, at a rate proportional to the amount that's in the bloodstream. So that's minus K12 X1. And then some of the drug is actually being reintroduced into the bloodstream from the brain, and that is at a rate proportional to the amount that's in the brain. That's plus K21 X2. And then finally, we have not taken into account that the drug is actually being introduced into the bloodstream from an outside source, like an IV or a pill, and that's going to be at a rate we'll call d of t. And so what you have here is you have, for each arrow designating where the drug is flowing into the compartment X1, you have a rate of proportionality that is proportional to X1 in most of those cases. And then finally, you have the drug just being introduced independently of how much is already in the bloodstream. Okay, so dx2 dt, okay, the rate of change of the amount of drug that's in your brain. Well, we're going to introduce some of the drug from the bloodstream at a rate K12 times X1. So that's a rate proportional to the amount that's in the bloodstream. And you can see, in fact, that this term is matching what is leaving the bloodstream. Okay, and then plus the amount that's leaving the brain and going back into the bloodstream at a rate proportional to the amount that's in the brain. So K21 times X2, and that of course should be negative because it's leaving the brain. So essentially, what is being introduced into the bloodstream from the brain here is actually leaving the brain here. Okay, and so now we have a system of two differential equations, and that is tracking how much of the drug is in your bloodstream and in the brain at any particular time. Now that's a simple compartment model that only has two compartments, but we could also have one with three compartments. Okay, so here I'm going to put one compartment in the middle. This is going to be where the drug is going to flow into your bloodstream. Okay, and we do have some of the drug is going to be directly leaving the bloodstream at a rate, let's say K1, and going to some system in the body that's excreting that drug. Okay, and then what we're going to do is that the drug can leave the bloodstream at a rate, say K1, 2, and it can go into what are called soft tissues. So the brain could be one of those soft tissues, okay? Or we could look at other organs, okay? But also the drug that's in the soft tissues could be absorbed back into the bloodstream at a rate K2, 1. Or we could actually have the drug kind of leave the soft tissues on its own, okay, into some other system of the body. We'll call that K2. But we can also have the drug flow from the bloodstream into hard tissues. Hard tissues are going to be like your bones. So that's going to be at a different rate than it would flow into, say, soft tissues. Okay, so here we have hard tissues. Okay, and then of course we can have the drug flow back from the hard tissues back into the bloodstream at a rate K3-1, but we won't have the drug flow out of the hard tissue. There's not a way for the drug to flow directly out of the hard tissue, out of the body. Okay, and that's a system with three compartments. We'll label these three compartments X1 for the bloodstream, X2 for the soft tissue, and X3 for the hard tissue. And then it's just a matter of setting up a set of differential equations to describe the amount of the drug in each of the three compartments. So dx1 dt, kind of following the same pattern that we used before, okay, where we're going to describe the rate at which the amount of drug in the bloodstream changes based on these arrows flowing in and out of the bloodstream. So this will be leaving the bloodstream directly, minus K1 X1, okay? Leaving the soft tissue, or leaving the blood for the soft tissues, minus K1 2 X1. Leaving the blood for the hard tissues, that's going to be minus K1 3 X1. Then coming back from the soft tissues will be plus K2 1 X2. Coming back to the blood from the hard tissues will be K3-1 X3. And then we have the drug being introduced into the body at a rate d of t. We can write the second equation, dx2 dt. Okay, the rate of change of the amount of drug in the soft tissue. Okay, looking at the arrows, we're going to have directly leaving the soft tissues at a rate K2 times X2. Directly leaving the soft, or going from the soft tissue back to the bloodstream, minus K2-1 X2. And then, of course, what's introduced into the soft tissues from the bloodstream, that's plus K1-2 X1. Then finally, we have the hard tissues, dx3 dt. And that will be what's leaving the hard tissues for the bloodstream, minus K3-1 X3, and then what is going from the bloodstream into the hard tissues, that will be K1, 3X1. And so here we have a system of 3 differential equations that describes the 3 compartments for the bloodstream, soft tissue, and the hard tissues. I do want to note for both of these compartment models, if you look at them here, you can see that both of the systems here are linear. Okay, so all of the terms x1, x2, and x3 are linear. Okay, we don't see any combination terms between x1 and x2 or x1 and x3. And both of these models are in fact going to be non-homogeneous. That is because we're going to have the drug being introduced at a rate d of t that's independent of the compartments x1, x2, and x3.